Let's look at the last lecture video on the index and logarithm, taking the natural log. Before that, we want to clarify certain things. There's a common law and then there's a natural law. The key difference here is that the common law comes with a base of 10. The natural law comes with a base of e, the exponential function. So in other words, we can write log e as the ln. So they are the same. That is why you have equal to sign here. You take note of the common log. If the base is not defined, you can always take it as the common log, that is 10, unless you have the base 2. This is not a common log. There is a normal logarithm you can go with. Okay. We still have some rules to play, or rules of the game. Now I want to help you out with the rules here. There's no difference between, if I use that word, I think I'm mistaken. The rules of the natural log is just as the rules of the common log. The difference here is the base. The difference here is the base. So in place of log 10, we are saying we have log e, and all other things remain the same. So follow me. If you go back to the log rules, log AB, what does it gives me? If the base is, they have log A plus log B. In the same way, this also gives me ln A plus ln B. So they are the same, just that the base has changed, nothing else changed. The rules are the same. In my log A over B, I know it is going to be log A minus log B, if you remember. So the same thing, it means this is going to give me ln A minus ln B. Do you remember this argument to the power rule? What do we have? It says bring P down and take log of the M. This is the same thing. So what do we have here? We'll have P ln of M. As simple as that. The rules are the same. You can look at the inverse property, the one-to-one property, as I have on my slide 14. But I want you to take note of these key rules. Okay. There's another interesting thing to look at. That is from the inverse and then the exponential log property. If I'm going through slide 14, that will be the fourth item and then the fifth item. So I want to move to slide 15 to explain that. There's a relationship between the exponential function and then the natural log. They are related, such that the exponential of the natural log is the same as the natural log of the exponential. I don't know how confusing this is, but they have an inverse relation. Inverse means they cancel out. So ln of exponential cancels out. Exponential of the ln cancels out. I have equal to x because there's an x here. So if they cancel out, it means I'll get x as the answer left. Let me use A. So this gives me A. That is the relationship between these two. Okay. Now let's apply the rules. I'll go through the first example. We want to find x. In maths, we're always finding x. We want to find x given this equation. The first thing everyone will do is to divide through by the 4, and that is what I have here. We want to find x. We can use the inverse property because the exponential and then the ln has an inverse relationship. The only way to clear this exponential is to take the ln of this guy here. So I'm taking the ln of both sides. So we take the ln, or we take the natural log of both sides. Why? Because we want to do away with the index here. And that's the only way we can have it. If I take the ln of both sides, you realize that I'll have, let me not rush through this example, I'll have ln of 7 on 4 equated to negative 3x. Why? Exponential length has a inverse relationship, and so simply my x can be negative 1 on 3 length of 7 on 4. That is how we use the exponential and the natural log relation. And so that is it. I think in the question I used negative 3 and solving I used positive 3. Sorry for the mistake. Now the second example, I have the expression given in length equated to some number. I still want to find my value for x. What can I do? Because there's a length, I can introduce the exponential. So I take exponential of both sides, exponential of this whole thing. So this means I'm taking the exponential of both sides to clear the natural log. If I do that, this guy goes away and I have that. And I also have exponential of my value here. Now can you find your x? Yes. By change of subject, I get 5.14 on that. I can use my calculator to punch it and then I'm good to go. So please, in applying the rules, you must take note of this relationship as well. I have a trial question here. You can, it says find t is the same thing. Okay, so to the problem of the day, you see a whole lot of things here. You don't need to be afraid, don't need to be confused. Take your time, read, extract, solve. So let's read. It says there's an experiment being done on bacterial growth culture, bacterial growth. We see a growth here. The word is a growth. Whether it is a decaying or increasing, we have to continue reading. The growth is an exponential growth. It means it's increasing. They are multiplying. We know with bacteria. So first, I see an equation given. So that is my extraction 1. Because it's blue, I don't want to still use blue. Let me use green. Extraction 1, I write my equation down. Extraction 2, I look at the terms defined in the equation. What is NT? What is N naught? What is K? What is T? They are well defined. So the problem, what is required of me to do? The first says that if the initial bacteria is 1,000, now you realize there are no N and K's here, they are words. It means if you neglect this aspect of the extraction, you can't solve the problem. So it means that M naught is given, the initial population is given to be 1,000. It says, and the growth rate is 0.2 per hour. What is the growth rate? It is K. Calculate the population after 5 hours. Time, T is given. We want to find N at 5. What do? You simply substitute the value for T into the equation. So N naught is given. I just have to find 5 here. So give me the answer in the comment section. What is the population of the bacteria after 5 hours? Don't forget, it is growing. And so I expect my answer to be greater than the initial population. So this should be greater than 1,000. I made this comment in the previous video. You must read, not just solve, and understand. If your final answer is less than the initial, because they are not decaying, they are growing, then there's a problem with your calculator. Okay. The second problem, what are we requested to do? It says if the population reaches 5,000, so now there's an increment in the population. How long did it take it to grow to this size? How long? How many hours did it take for the bacteria to grow to 5,000? So I already have my equation given, the model. I'm looking for T. That's what I'm looking for. So if you don't know what you're even finding, you don't even know how to solve that problem. Do you expect t to be greater than the initial case or more, or less? That's the question for the goals, if you understand the problem. Because I want t, the first thing will be to divide both sides by n0, and that is what I have here. T is an index here, so I want to find a way to clear it or have it for myself, and the only way is to take the natural log of both sides. So I have the natural log of this and then the natural log of that. Because they have inverse relation, this cancels out and then I get just this guy, but still my ln will be on here. And then I can simply find t by change of subject. T is 1 over k ln of that. And so how many hours or minutes did we have? Don't forget, because they are growing, in the initial stage it was 1000, now it is 5000. What is the time? Okay, so you can leave your answer in the comment section. And this brings us to the end of our indices and logarithm. We move on to sets. Enjoy the day.